I'm Jian-Hua Yan from MediaTek. I represent my two colleagues, Meiling Qi and Yunyang to propagate this report, Strategies and CDC False Alarm Rapid Location. With the increment of chip design complexity and the application of low-power technology, generated more and more clock domains and report millions of CDC violation paths. As shown in pictures, from 2004 to 2020, the number of clock domains rose from 180 to 1,163. The number of violations rose from 1.29 million to 7.26 million. On the other hand, more and more designers cooperate to develop one project. If one designer sees millions of violations, it will be a disaster for project execution. How to claim millions of CDC violations with a limited time is a critical issue. During the implementation of CDC, we analyzed the initial violation reports of multiple projects. We find that about 80% of violations are false alarms. We can use the following four methods to quickly clear false alarms and get a more accurate CDC report. The first, clarify false asynchronous clock groups. The second, point out high-fan-in and high-fan-out registers. The third, auto-generate reviews for CDC safety-proven design. The fourth, fix invalid CDC constraints from legacy projects. Let's first look at the impact of the inferred clock and CDC violation. The inferred clocks are not user-specified clocks, but true inferred clocks. Default, the CDC2 will consider these uninspected clocks as asynchronous clocks. If this inference is wrong, a large number of false alarms will be generated. The more violations between two clock domains, the higher the possibility that they are actually synchronous. Figure 2 shows a typical run-inferred clock. We need to set the select port of the max to constant 0 to fix this inferred clock and remove a large amount of violations. Table 2 shows the violations caused by inferred clocks of three projects. About 48% to 67% of violations are related to inferred clocks, so that classify the inferred clocks domain becomes the primary task. In Project A, the top 10 violations grouped by teacher ultra clock pairs are listed in Table 1. The violations generated by the first three clock pairs account for 24%. So, we should clarify the top 10 inferred clock pairs listed in Table 1. High-fan-in and high-fan-out are the main reasons for false violations. The high-fan-out register is the flip-flop on the left of Figure 3. It has multiple target registers. The high-fan-out registers are mostly function configured registers. These registers have hold stable value when the function units are working. So, we don't worry about the CDC issue on these registers. We can set these registers to stable signal and no longer trigger this path. The high-fan-in register is a flip-flop on the right in Figure 3. It has multiple source registers. Such registers may be debug function registers, and usually we do not care about the CDC issue and such results. So we can ignore the CDC path, check on these results. Focus on Table 3. We find the violations caused by the hyphen outer register account for more than 46%. So once the designer firstly solves the top 10 registers, huge violations will be removed. The bus fabric relies the interaction among multiple blocks and uses a handshake protocol to ensure CDC security. Normally, the bus fabric will generate many CDC violations. In Table 4, the number of violations caused by bus fabric are from 5% to 21%. The infrabus design is generated by an EDA tool. Meanwhile, the EDA tool can generate the CDC design spec for bus fabric to describe its CDC strategy. We import the CDC design spec to automatically remove these violations. We use CDC design spec fields to describe the design intent of CDC path. These fields are reusable, but we find that the CDC tool reports many error messages about the spec fields. The CDC constraint commands have been lost, and the CDC tool reports loss of false alarms. For example, as shown in Figure 5, upgrade from Project 2 to Project 1 to Project 2. The instance named ufunction unite is not changed, but its hierarchical path is changed from your subspace top, your function top, your function unite, to your subspace top, your function unite. In Project 2, after imported the qualified CDC design spec, CDC 2 report not found signal, your subspace top, your function top, your function unite, all 2 times. From Project 1 to Project 2, the module top MPU low only changed the module name. However, after imported the reusable CDC design spec file, CDC 2 report not found module name, top MPU low. These errors are obvious. We can use script to automatically analyze these changes from Project 1 to Project 2, and then apply the difference to reusable CDC design spec files to generate revision openings. The designer can quickly update the new CDC design spec files based on these openings. Using the above 4 strategies, and we can quickly remove the CDC false alarm. In our actual project, after clarifying the main infra clock, the number of violations was dropped from 7 million to 1 million. After applied hyphen in and hyphen out registers, the number of violations was dropped to 500,000. After applied CDC design spec of bus fabric, the violation was dropped to 200,000. After fixed a sample error in the design spec, the number of violations was dropped to 100,000. At this time, the remaining 100,000 violations can be distributed to the respective owners to do further check. The Table 8 displayed the execution process of the 3 previous projects. The number of initial validations are 7.5 million, 2.7 million, and 2.2 million. Using the above 4 strategies, after 2 weeks, the number of validations respectively dropped by 97%, 91%, and 88%. They successfully achieved the expected growth. Thanks.